Hello, everybody. Today I'll be introducing a neck movement classification algorithm using surface electromyography. So first of all, this is actually part of a larger project, which is currently under investigations by our group, which is to develop this wearable neuromodulation device for treating cervical dystonia. So what is cervical dystonia? It's actually a type of neurological disorder, which is characterized by involuntary neck muscle contractions. So when the dystonia occurs, it would lead to an irresistible abnormal neck posture. And the previous studies by our group has shown that with vibrotactile stimulation, which is a type of vibration, it can help the patients to restore a normal head posture. So in order for this wearable device to apply vibration on the target muscles, we need to firstly classify neck movements. So this motivated us to develop this linear algorithm to classify neck movements with only a limited amount of sEMG electrodes. In this study, we have recruited 5 participants. To measure muscle activity, we have 4 sEMG electrodes attached to 2 muscles, the sternocleidomastoid and trapezius. So during the data collection process, the participants were asked to complete sequentially 10 movements, including 6 single-planar movements, which are forward and backward flexion, left and right head rotation, left and right lateral flexions, and then 4 multiplanar movements, which are right and left forward tilt and right and left backward tilt. So each movement was repeated for 3 times. The data of the first repetition was set as the baseline, and then the following 2 repetitions were firstly segmented into 128 millisecond intervals and then set as test sets. So the data were firstly filtered with a 100 Hz low-pass filter, and then in the feature extraction process, we firstly computed a 10x4 reference matrix with the baseline data, and then for each unlabeled interval, we computed this 1x4 interval matrix. Then to classify each unlabeled interval, we then cross-correlated this interval matrix with the reference matrix, which gives us 10 correlation coefficients corresponding to 10 movements. So the interval label was set to the class with the highest correlation coefficient. And furthermore, we have a correction algorithm following after to boost up the accuracy. To evaluate the performance of our proposed algorithm, we compared it to 2 commonly used approaches, which are the linear discriminant analysis and a 3-layer fully connected artificial neural net. So in the table, you can see that our proposed algorithm showed approximate accuracy with artificial neural net in terms of classifying both single-planar movements and multiplanar movements. And furthermore, in this confusion matrix, you can see that the classification accuracy varies among different movements. So for some neck movements, the classification accuracy could drop down to approximately 60%. Well, a possible explanation for this could be that when we bring in the multiplanar movements, they are more difficult to classify compared to single-planar movements because they might involve deeper muscle groups. So these deeper muscle groups, for example, the splenius capitis, might not be able to be measured by the surface sEMG electrodes. But overall, our algorithm showed decent accuracy in terms of classifying neck movements. And furthermore, its linearity and simplicity enables it to be embedded in the low-cost processors. So thank you all for listening. And if you have any questions, feel free to ask.